Imagine standing on a beach somewhere in what we now call Spain or Morocco. It's a warm evening, waves are lapping at your feet, the Mediterranean stretches out in front of you, enormous and blue and ancient, exactly the way it's always been. Except one day, roughly 6 million years ago, it wasn't. One day the sea just started disappearing. Not a storm, not a tsunami, something slower and stranger, and almost completely impossible to wrap your mind around. The water began to withdraw, year by year, century by century, until one of the largest bodies of water on Earth had essentially vanished. Left behind was a basin deeper than almost anything on the planet's surface, a hot, salt-crusted alien landscape sitting miles below the surrounding land, a place where rain would evaporate before it hit the ground, a wound in the Earth so vast and so strange that even today, scientists are still piecing together exactly what happened. And then, after millions of years of absence, it came back. Not slowly, not gradually, all at once. The leading models suggest the Mediterranean may have refilled in a matter of weeks, possibly less. An amount of water so staggering, moving so fast that it would make every flood in recorded human history look like a leaking faucet. That's the story we're going to tell tonight. And here's the thing that makes it even more extraordinary. We almost didn't know this happened at all. There are no human witnesses. There are no written records. Just the Earth itself quietly holding the evidence. Salt formations thousands of feet thick buried beneath the seafloor. Ancient canyon systems carved into bedrock by rivers desperate to find a level that no longer existed. Cores of sediment drilled up from the deep sea that contain layers telling a story so unusual that when scientists first read them, some didn't believe what they were seeing. You're going to hear about something called a salt giant, about a canyon beneath the Nile that makes the Grand Canyon look modest, about a narrow gap at the western edge of the Mediterranean that became, for a brief and violent moment, the most consequential waterfall in the history of this planet. None of it explained just yet. Each piece of evidence has its own chapter. We'll get there. But the core mystery is this. How does an entire ocean disappear? What has to go wrong, or right, with the plumbing of a planet for something like that to happen? And once it's gone, what does the world look like on the edge of that absence? What survives? What doesn't? These are the kinds of questions that don't have simple answers, but do have incredibly satisfying ones if you follow them all the way down, which is exactly what we're going to do tonight, slowly, step by step, through deep time and shifting continents and a sea that forgot it existed for a few million years. If you're listening to this to fall asleep, that's genuinely why I make these long, slow, fascinating stories about things that happened so far back that the strangeness of them becomes almost dreamlike. So make yourself comfortable. Wherever you are right now, whatever time it is, you're exactly where you're supposed to be. And speaking of that, tell me where you are and what time it is when you're listening to this. Drop it in the comments. I actually read them. It's always something like Lagos at midnight, or Melbourne just before dawn, and somehow that never gets old. The Mediterranean is waiting. Let's go back 6 million years and watch the sea disappear. Before we get to the disappearing act itself, we need to spend a little time with the world as it existed before, because the Mediterranean Sea, the one you can find on any map, the one that shaped Roman trade routes and Greek mythology, and practically everything that came after, that particular body of water was never guaranteed. It didn't have to be there. It exists because of a very specific set of geological arrangements, and those arrangements are more fragile, more contingent, more dependent on narrow corridors and unlikely combinations of circumstances than most people ever stop to consider. Think of the Mediterranean not as an ocean, but as a basin, a large, almost enclosed bowl sitting between two continental landmasses, Africa to the south, Eurasia to the north, with only the thinnest connections to the wider ocean world. Water gets in through gaps. Water evaporates from the surface. The whole system stays alive only because inflow and outflow are roughly balanced. Take away the connections and you don't have a sea anymore. You have a problem. The Mediterranean loses more water to evaporation each year than it receives from rainfall and rivers combined. That's not a minor imbalance, that's a structural deficit. The only reason it doesn't simply shrink away over centuries is that Atlantic water flows in constantly through the Strait of Gibraltar, replenishing what's lost. Close that gate, or even significantly narrow it, and the countdown begins. 6 million years ago, that gate was being squeezed shut. Not quickly. Nothing in plate tectonics happens quickly. at least not by human standards. Africa and Eurasia had been moving toward each other for tens of millions of years, a slow, grinding collision that built the Alps, raised the Pyrenees, and gradually reshaped the connections between the Atlantic Ocean and whatever ancestral sea sat in the Mediterranean basin. By the late Miocene, which is the geological epoch we're talking about, that movement had narrowed the available corridors dramatically. And here's something worth sitting with for a moment. The coastlines of that world looked almost nothing like the ones we know. The Strait of Gibraltar as we know it didn't yet exist in its current form. There were other seaways, other routes through what is now Spain and Morocco, through the region geologists call the Betic Corridor in the north and the Riffian Corridor further south. These were the Atlantic gateways of the time, broad marine connections that allowed ocean water to flow freely into the Mediterranean basin. And one by one, as Africa continued pressing northward, they were closing. The timing of this closure is something scientists are still working out, and that uncertainty is worth naming directly. Different reconstructions of the ancient geography put the final closure of these corridors at slightly different moments. Some models suggest the Betic corridor was already closed by around 7 million years ago. Others place the critical thresholds closer to 5.96 million years ago. The sediment records are clear that something dramatic was happening in that window, but the exact sequence of which gateway closed when and how completely is still debated. The Earth keeps its records in rock and salt and fossil chemistry, and reading those records requires interpretation. What seems clear is this. The late Miocene Mediterranean was already a sea under stress. The climate was shifting too, becoming drier and more seasonal in ways that would have increased evaporation and reduced river input. The ice sheets at the poles were waxing and waning, pulling sea levels up and down in cycles that could open or narrow shallow marine passages by meaningful amounts. A corridor that was navigable during a high stand of sea level might become a mudflat during a low stand. The plumbing of the ancient Mediterranean was, in other words, profoundly sensitive to small changes. This is the distinction that matters more than almost any other in this story. Tectonic processes move at the pace of centimeters per year. A mountain range takes millions of years to build. A continental collision takes tens of millions more to resolve. But hydrological consequences, what happens to the water when the geography changes, those can unfold on completely different timescales. Geological slow burn setting up a hydrological sudden event. The tectonic squeeze takes millions of years. The sea level response to losing a gateway could take thousands of years, and the final catastrophic refilling, as we'll get to, may have taken weeks. That contrast, the deep patience of plate tectonics against the explosive urgency of water finding its level, is the essential rhythm of this entire story. There's one more thing worth understanding about the Mediterranean basin itself before we proceed. It's deep, remarkably, improbably deep. The floor of the western Mediterranean sits around 3,000 meters below sea level in places. The eastern basin goes deeper still. This matters enormously because when you seal off an evaporating sea, the surface doesn't just drop a little, it plunges. The basin is deep enough that losing its Atlantic supply would eventually expose bedrock that hasn't seen open air since before humans existed. Rivers flowing into such a basin would find themselves chasing a shoreline retreating thousands of meters below them, cutting canyons of extraordinary depth just trying to reach the surface of a shrinking sea, which is exactly what the evidence suggests happened. But we're not there yet. For now, hold on to this image. A warm late Miocene world, roughly 6 million years ago, with different coastlines, unfamiliar mountain profiles, a Mediterranean basin that still holds water but is already more isolated than it used to be. Africa still pressing north, the corridors still narrowing, and the sea, blue and warm and ancient, sitting on the edge of something it has no way of knowing is coming. The crisis had a name. Scientists call it the Messinian Salinity Crisis, and it begins quietly, the way most catastrophes do. The name comes from Messina, the Sicilian city that sits at the narrow water between the island and the Italian mainland. Geologists working in the region during the 19th century found something strange in the rock record there. Layers of mineral deposits that had no business being where they were, salts and gypsum and other evaporate formations sitting in sequences that spoke of extreme environmental conditions. They named the geological age for the place, the Messinian, and the crisis that defines it carries that name still. the Messinian Salinity Crisis. Roughly 5.96 million years ago, give or take, with certain effects accumulating both before and after that threshold, the Mediterranean Sea began to transform into something that had no modern equivalent, something that would have been, to any observer capable of perceiving it on the right timescale, completely terrifying. To understand what happened, you need to understand what happens to any body of water that loses its connection to replenishment while evaporation keeps running. Evaporation doesn't take water and leave everything else behind cleanly. What it actually does is concentrate. Every time a water molecule escapes the surface as vapor, the salt it was carrying stays in the basin. The water level drops a little. The salt concentration rises a little. Now the next water molecule that evaporates leaves behind slightly more salt per unit of remaining water. The process is self-reinforcing in the worst possible way. Given enough time and a restricted enough inflow, a sea doesn't just shrink, it transforms, first into something like the Dead Sea, hypersaline, hostile to most life, strange and thick and still. Then, if conditions hold, into something stranger still. When salinity climbs high enough, minerals begin to precipitate directly out of the water. Calcium carbonate comes first, then gypsum, then halite, which is ordinary rock salt, then even more exotic compounds as the chemistry pushes into ranges you don't encounter in a normal ocean. These minerals sink and accumulate on the seafloor in layers. Geologists call these deposits evaporates, and when they accumulate over vast areas, over thousands of years of concentrated dying, the layers can reach extraordinary thicknesses, 3 kilometers in places beneath the modern Mediterranean, sometimes more. Geologists have a term for deposits of this scale. They call them salt giants, and the Mediterranean salt giant is one of the largest ever identified on Earth. Roughly 1 million cubic kilometers of evaporate material buried beneath the seafloor, a record of what happens when an inland sea is left to cook. That number is worth sitting with. 1 million cubic kilometers of salt. Salt that was once dissolved in an ocean. Salt that came out of solution because there wasn't enough water left to hold it. The sheer volume of it is a clue, an almost accusatory one, pointing back at an event of enormous duration and severity. But here's where the story becomes more nuanced, and the nuance matters. A partially restricted sea and a nearly completely isolated sea are not the same thing. They produce different outcomes, different kinds of evidence, and different degrees of catastrophe. A Mediterranean that still received a modest trickle of Atlantic inflow might have become hypersaline without ever fully drying out, its surface dropping, its chemistry shifting, its ecosystems collapsing in stages, but always retaining some body of liquid water, always depositing evaporates from a brine rather than exposing bare rock to open air. A Mediterranean that was more completely sealed off faces a different fate. Evaporation doesn't stop, the basin floor is deep. The water has to go somewhere, which is to say it goes into the atmosphere, leaving its minerals behind, and eventually the surface drops far enough that you're no longer describing a sea at all. The debate between these two scenarios, partial desiccation versus near total drying, is one of the genuine open questions in this field. The evidence supports elements of both at different times and in different parts of the basin. The Western Mediterranean and the Eastern Mediterranean may have behaved differently from each other. There may have been periods of partial reconnection, brief pulses of Atlantic water sneaking back in, temporarily refreshing the brine before the restriction tightened again. The crisis was probably not a single smooth slide from normal sea to salt flat. It was more likely a complicated oscillation, the basin breathing in and out in shallow, increasingly desperate cycles. What drove the crisis deeper was climate. The late Miocene was not a stable time. The global climate was shifting toward cooler, drier conditions, a long-term trend driven by changes in ocean circulation, the growth of Antarctic ice, and the rearrangement of continental positions that altered how heat moved around the planet. For the Mediterranean specifically, this meant less rainfall, more intense summer evaporation, and reduced river discharge into the basin. The rivers still flowed, the Nile precursor, the Proto-Rhone, rivers draining the Alps and the Atlas Mountains, but their contributions were shrinking relative to what the atmosphere was pulling off the surface. The structural deficit that defines the modern Mediterranean, more evaporation than precipitation and rivers combined, was getting worse. The sea was not just losing its Atlantic supply, it was losing its fight with the sky. Sea level oscillations tied to polar ice growth made everything less predictable. A drop in global sea level of even a few dozen meters could transform a shallow marine corridor into dry land, shutting an Atlantic gateway as effectively as any tectonic movement. Then ice melts slightly, sea level rises, the corridor reopens briefly, a pulse of saltier than Atlantic water refluxes, the chemistry in the basin shifts again. The system was flickering in and out of connection, never quite stable, always trending toward the same outcome. Which brings us to the central question that researchers are still debating, the one that shapes everything else in this story. When the Messinian Salinity Crisis reached its most extreme phase, did the Mediterranean simply become a vast hypersaline lagoon, terrible for life but still wet? Or did it go further? Did the water actually disappear? If you could peel the modern Mediterranean like the lid off a pot and look straight down into the basin, you wouldn't see a simple stack of mud and sand, you'd see a pattern. Thick pale bands of gypsum and salt, darker, muddier intervals, repeated over and over like the heartbeat of a sick ocean. Those patterns are the reason we know something extraordinary happened here. Evaporates like gypsum and halite aren't shy about the conditions that make them. They're picky minerals. Gypsum needs water that's already much saltier than normal seawater. Halite, ordinary rock salt, needs it saltier still. You don't get these minerals settling out of a healthy ocean in any serious quantity. You get them when the water is trapped, when the sun has had too much time, when evaporation has pushed the chemistry to the edge. And it's not just that they're present under the Mediterranean, it's how they're arranged. In cores drilled from beneath the seafloor, and in cliffs where ancient Messinian rocks are exposed on land, geologists see stacked sequences. A thin layer of fine mud, sometimes with traces of normal marine life. Above that, a thicker layer of gypsum crystals, sometimes growing in delicate blade-like forms. Above that, purer halite, massive and structureless or laid out in rhythmic couplets. Then, again, mud. Again, gypsum. Again, salt. Flooding, concentration, drying, reset. The repetition is the important part. A single thick blanket of salt could, in theory, be explained by one long, stable, hypersaline phase. But when you see packages of evaporates separated by thin returns to more normal sediment, it suggests something else. A basin that's being refilled and concentrated in cycles, sometimes with water coming back in from the Atlantic, sometimes from rivers that were briefly able to build shallow lakes on the exposed floor before the sun stripped them away again. In some places you can zoom in further. Under the microscope, the gypsum layers resolve into tiny laminae, light and dark, each couplet potentially marking a seasonal shift. A wet season when a little more water could dilute the brine, a dry season when the surface dropped and crystals grew faster. You're looking at years, centuries, even millennia of slow, painful oscillation encoded in millimetre-thick bands. The chemistry tells part of the story. The tiny fossils locked in those layers tell another. Most marine sediments are full of microfossils, foraminifera, tiny shelled protists that float in the water column or live on the seafloor, coccolithophores, minute algae that build plates of calcite. Their shells rain down continuously, building up carpets of microscopic skeletons that carry a record of temperature, salinity, and depth. During the Messinian, that quiet snow of skeletons changes abruptly. In some layers, especially just before the onset of the crisis, you find normal open marine assemblages, a healthy mix of species that prefer well-oxygenated water columns of moderate salinity and stable depth. Then those assemblages thin. Species that are intolerant of rising salinity disappear first. Others hang on a little longer, replaced by hardier forms adapted to stressed environments. Eventually, in the heart of the evaporate sequences, the microfossils almost vanish, or they reappear only as forms that can tolerate extreme conditions, hypersaline lagoons, shallow water that may have dried to crust between pulses of inflow. In some intervals, you see freshwater or brackish water species showing up on top of or between marine layers, tiny fossils that usually live in lakes and rivers suddenly appearing hundreds of meters below where the Mediterranean surface once stood. Their presence is a quiet but powerful clue. It suggests that parts of the basin weren't simply a deep stagnant brine. They were at times shallow enough or compartmentalized enough to host near freshwater conditions. Lakes on what had once been sea floor, estuaries perched halfway down a continental margin. places where river water pooled temporarily in depressions cut off from the main body of whatever hypersaline residue persisted elsewhere. And just as the microfossils speak when they're present, they speak when they're absent. Long stretches of sediment nearly devoid of normal marine plankton point to times when the free circulating Mediterranean Ocean simply wasn't there, not in any form recognizable to the tiny organisms that usually mark its existence. The rocks don't just record what was settling out of the water, they also record what the water was doing to the land. Along the margins of the ancient basin, there are surfaces that look wrong for a stable sea. Steep, incised valleys cut into older sediments and bedrock, abrupt steps in the landscape that mark ancient shorelines hundreds, even thousands, of meters below present sea level. Infilling sediments that fine upward from coarse gravels and breccias, broken, jumbled rock, into calmer, finer deposits. These are erosional surfaces and they carry their own message. At some point water levels fell dramatically. When a large body of water drops quickly, rivers respond with enthusiasm. They gain potential energy. They start cutting downward, carving canyons into the exposed continental margins, chasing the new, lower base level. The Nile, the Rhone, and other Messinian rivers appear to have done exactly that. Evidence suggests they incised far below their modern valley floors, bored their way deep into what is now the submerged continental shelf, and perhaps even further into what was then an exposed basin floor. You can see this in seismic profiles, acoustic cross-sections of the subsurface, where V-shaped cuts slice down into older, relatively flat strata, later buried under younger sediments when the sea returned. You can see it on land, where remnants of these canyons and terraces still survive, draped now by younger deposits but unmistakable once you know what to look for. Taken together, the evaporate sequences, the microfossil shifts, and the erosional surfaces form a three-dimensional puzzle. To turn that puzzle into a timeline, you need tools that can pin specific layers to specific moments in Earth's history. You can't carbon date 6 million-year-old salt. But the planet offers other clocks. One of the most reliable is the magnetic field. Earth's magnetic field flips polarity at irregular but well-documented intervals. North becomes south, south becomes north, and the change is recorded in certain minerals as they settle and lock into place. Tiny magnetic grains in clays and volcanic ashes behave like compass needles as they form, aligning with the prevailing field. When you cool or bury them, they freeze that direction in. By sampling Messinian sediments and measuring the orientation of these mineral compasses, geologists can identify intervals of normal and reversed polarity. Those intervals can then be matched to the global geomagnetic polarity timescale, a kind of barcode of flip stretching back tens of millions of years. If a particular evaporate sequence sits between two known reversals, you can say with some confidence when it formed, at least within a few 100,000 years. Another clock is biological. Different species appear and disappear from the fossil record at known times. This is biostratigraphy. If a particular kind of planktonic foraminifer or calcareous nanoplankton is present in a layer just below the first gypsum bed, and you know from other parts of the world that this species vanished at, say, 6 million years ago, that gives you a bracket. If another species that only appears after 5.3 million years shows up above the last salt, that gives you another. Then there are ash layers. The Mediterranean region has always been tectonically active, and during the late Miocene, volcanoes in Italy, the Aegean, and beyond were periodically dusting the basin with fine volcanic ash. These ash layers are geological gifts. They can often be dated directly, using the radioactive decay of isotopes like argon in the volcanic minerals. When a datable ash lies just beneath or just above a key Messinian horizon, it pins that horizon in time with far greater precision than magnetic flips alone. By cross-correlating magnetic reversals, fossil assemblages, and ash dates, researchers have built a remarkably detailed chronology of the Messinian Salinity Crisis. They can tell when the first major evaporates appeared, when conditions intensified, and when the flood that ended it all likely began. But even with all these tools, interpretation is not straightforward. The same broad suite of rocks, evaporates, muds, erosional surfaces can emerge from different basin configurations. A shallow, wide, but still mostly flooded Mediterranean with strong vertical salinity gradients could, under the right climate, also deposit thick salts, especially in deeper subbasins. Local restrictions, sills and ridges separating parts of the basin from each other, might create miniature death traps that fill and dry repeatedly without requiring the entire sea to vanish. Some of the supposed canyon-like erosional features might in principle form under conditions of strong bottom currents or localized tectonic uplift rather than a basin-wide drop. Certain microfossil assemblages could reflect unusual water stratification, dense hypersaline bottom layers overlaid by fresher surface waters rather than complete desiccation of the deep. There is an active, ongoing conversation in the literature about how far the crisis went, whether the basin floor ever truly stood thousands of meters below global sea level as exposed land, or whether pockets of deep brine persisted like ghost seas beneath lower standwater in adjacent regions. What almost everyone agrees on, though, is that the rocks record a Mediterranean that was pushed far outside its normal operating range. You don't stack kilometre-thick salt giants across 500,000 square kilometres without severe, prolonged disruption. You don't see marine microfossils blink out over vast areas, then return without some form of near collapse and recovery. You don't carve deep valleys into continental margins without a dramatic change in base level. The clues are circumstantial, but there are a lot of them, and they converge on the same unsettling picture: a sea that lost its balance, lurched through cycles of drowning and exposure, and came closer to disappearing than any other modern ocean basin we know. And those clues point us forward, toward an even stranger part of the story. Because if the Mediterranean really did sink into a deep, partially empty basin, with rivers plunging down to a floor far below the present sea level, then the way it came back, to anything like the sea we know today, could not have been gentle. It would have required a flood on a scale that stretches imagination, a sudden refilling of a basin that had spent hundreds of thousands of years dying by degrees. Imagine for a moment that the Mediterranean really did fall. Not just a gentle lowering of the shoreline, not a few meters lost to climate or glacial cycles, but a plunge. A basin whose surface dropped hundreds, maybe more than 1,000 meters below the global ocean. A sea pulled down. If something like that happened, the land around it would have noticed. Because coastlines are not passive, rivers pay attention to where they end. In geomorphology, there's a simple, brutal idea called base level. For a river, base level is the lowest point it can erode down to. Most of the time that's sea level. Change that, and the river's whole behaviour changes with it. Lower the base level suddenly, and rivers sharpen like knives. They cut downwards. They incise their beds. They stop meandering lazily across floodplains and start digging canyons, racing to catch up with the new lower outlet. That's the response you'd expect if the Mediterranean surface dropped by hundreds of meters during the Messinian, and in the rocks, along the old margins of that troubled sea, we see something that looks very much like this reaction. Take the Nile. Today, the Nile flows gently across its broad floodplain, then fans into a delta before it slips into the modern Mediterranean. It's slow, dignified, an old river on a low-gradient path. But beneath the sediments of that delta, hidden under layers of younger deposits and the modern seafloor, there is another Nile, a ghost river. Seismic surveys and drilling have revealed that during the Messinian, the Nile carved a valley far deeper than anything the modern river requires. Its buried canyon cuts down hundreds of meters below present sea level, slicing through older strata on the continental shelf and continuing basinward toward what would, at the time, have been exposed Mediterranean floor. To drive a river that deep, something has to pull its base level down with it. You can tilt the land upward, you can drop the outlet, or you can do some combination of both. But you cannot get that kind of incision while the downstream end is sitting comfortably near present sea level, and the Nile wasn't alone. In southern France, the Rhône shows a similar story. Under its delta, seismic profiles reveal a steep, V-shaped valley cut into older Miocene sediments, later backfilled when the sea returned. Around the Iberian Peninsula, other rivers feeding into the western Mediterranean preserve signs of Messinian overdeepening. The pattern repeats along different margins, at different scales, rivers cutting too far too fast for ordinary conditions. It's as if, all around the rim of the basin, the rivers suddenly got permission to fall. When that happens, landscapes don't change politely. Picture a river like the early Nile confronted with a Mediterranean whose surface has sagged hundreds of meters below its old shoreline. The last stretch of the river, which used to meet the sea in a broad estuary, is suddenly hanging in the air above a distant, deepening basin. The gravitational potential energy of that water, its desire to fall, is no longer balanced by a nearby sea. So the river starts carving headward, working its way upstream, chewing into its own bedrock and sediments, lowering itself to match the new base level far below. Waterfalls may form. Steep nick points migrate inland as slabs of rock and sediment collapse, are carried away, and replaced by lower, steeper channels. Over thousands of years, this process can sculpt enormous canyons. The Colorado River did it to the Colorado Plateau when tectonic uplift raised the land. During the Messinian, it appears that several Mediterranean rivers did something analogous, not because the land rose so dramatically, but because the sea they flowed into fell. At least, that's one interpretation. There's another possibility. Maybe some of the land around the Mediterranean rose instead. The region is tectonically restless. Plates collide, microplates twist and jostle, fault blocks tilt. Uplift can, on its own, steepen river gradients and trigger incision. If large areas around the basin were pushed upward during the late Miocene, rivers would have responded by cutting downward to regain equilibrium, even if the Mediterranean surface itself didn't drop as much as some models suggest. So when we see deeply incised valleys buried beneath today's coastlines, we're left with a puzzle. Did the sea fall? Did the land rise? Or did both happen together in a complex choreography of tectonics and hydrology? For the Nile, some researchers argue that tectonic warping of northeast Africa could explain a portion of the depth. For the Rhone, local uplift around the Alps and the opening of the Liguro-Provençal basin likely contributed. But even when you factor in reasonable amounts of tectonic movement, there is still a lot of incision to account for, especially when you stack the evidence from multiple rivers around the basin. That's where the drawdown hypothesis becomes tempting. If the Gibraltar Gateway had become restricted or closed, if evaporation outpaced any limited inflow, the Mediterranean surface would have started to drop. As it did, rivers feeding the basin would have incised. Their canyons would have lengthened and deepened, chasing the receding shoreline as it migrated downslope toward the central depressions. In some reconstructions by the height of the crisis, the Mediterranean is not a single body of water at all, but a patchwork, separate sub-basins partly filled with brine lakes at different levels, each shrinking and refilling on its own schedule. Between them, long slopes of exposed continental margin descend towards salt-encrusted flats and isolated pools of thick, oily brine. You can imagine standing on what is now the Spanish or North African coastline, and instead of seeing a continuous sea, you look out over a vast descending desert of rock and salt. Hundreds of meters below, hazy in the dry air, lies a shrunken lake, the remnant of the western Mediterranean, its surface glinting dully under a ferocious sun. The air smells faintly of sulphur and salt. Heat shimmers. Somewhere out on that floor, rivers like the ancestral Nile and Ebro and Rhone converge into sickle-shaped deltas, not at sea level, but at altitudes deep below it. Closer to the margins, the slopes are cut by canyons. Some of these start as simple river valleys, but deepen until their walls are steep, perhaps even cliffed in places. Erosion gnaws at them from above when rare storms send flash floods pouring down. From below, the periodic rise and fall of whatever brine pool sits at their mouth undercuts their lower reaches, encouraging further collapse. Over tens or hundreds of thousands of years, these valleys extend out across what used to be continental shelf, then down into the formerly deep basin. Today, many of these ancient canyons are buried. Some have been modified by later glacial and interglacial cycles, others are masked by younger sediments, but traces remain, etched into the subsurface like scars, over-deepened channels, unconformities where young fill rests directly on much older rocks, abrupt breaks in slope that line up at similar depths around different parts of the basin. There are even features on the modern continental slopes that look like submarine canyons, deep narrow cuts that extend from river mouths into the deep sea, that may have been initiated or dramatically modified during periods of low Messinian sea level. In our current world, these canyons help funnel sediment and turbidity currents from shelf to abyss. In the world of the Messinian drawdown, they may have been partly subaerial, carved by rivers racing down toward a distant depressed base level. That image, of rivers running not toward an ocean, but toward a series of sunken, shrinking lakes, has power. It explains, in a simple and physically intuitive way, why we see such intense incision in the subsurface records of the Nile, the Rhone, and other systems. It ties the geomorphology to the evaporates, the missing microfossils, and the broader narrative of a basin destabilized by lost connection to the Atlantic. But as with everything in this story, the evidence can be read more than one way. Some researchers emphasize that uplift and subsidence patterns around the Mediterranean are complex and still imperfectly constrained. A valley that looks over-deepened under one tectonic model might be more modest under another. Others point out that strong bottom currents, density flows along steep slopes, and localized fault activity can also sculpt canyon-like forms without requiring a basin-wide desiccation event. There is debate over exactly how far below global sea level the Messinian Mediterranean surface fell. Some reconstructions put the deepest exposed areas more than a kilometre down. Others suggest more modest drops, perhaps a few hundred metres, with residual deep brine bodies persisting throughout the crisis. In those scenarios, parts of the central basin never fully dried. Instead, they hosted dense, stagnant hypersaline pools while the margin swung between shallow water and exposure. In that kind of stepped landscape, base level for a given river wouldn't necessarily be the deepest part of the basin. It might be the level of a nearer sub-basin or perched lake, itself separated from deeper depressions by sills of uplifted crust or thick salt. The rivers would still cut, still respond to falling water levels, but their incision patterns would be more complex, their canyons segmented by changing thresholds. When geologists argue over these details, they're really asking, how empty was the Mediterranean, and where exactly did the water go? The incised valleys and buried canyons don't give us a single unequivocal answer. They can't say, on their own, whether the basin floor was a continuous desert of salt or a mosaic of lakes and brine pans. They can't fix the precise depth of the lowest surfaces. What they do say, with considerable force, is that base level fell dramatically somewhere downstream of these rivers. Whether that fall was due mostly to sea level drawdown within the basin, to uplift of the surrounding land, or to some interplay of both, the rivers record a sharp change. They remember a time when the Mediterranean stopped behaving like a stable ocean and became something stranger. Salt flats that crackle underfoot, marginal cliffs scalloped by retreating waterfalls, isolated toxic lakes slowly concentrating under a pitiless sun, canyons that begin near modern coasts but end far below any reasonable present shoreline. All of these are pieces of the same puzzle, arranged in rock instead of on paper. They don't demand a fully dry, 1,000-metre-deep void where the Mediterranean now lies, but they make a strong case for a basin that was, at least in places and times, profoundly drawn down, enough to rewire the rivers, reshape the margins, and leave behind canyons large enough to survive even after the sea came back. And that's the thread that leads forward. Because however far the water fell, however complex the patchwork of brine lakes and exposed shelves really was, eventually something had to change again. The rivers could chase a falling base level for only so long. At some point the gate at Gibraltar would open. At some point the Atlantic would find a way in. When it did, those same canyons and incised valleys, the scars of drawdown, would become pathways, channels ready-made to funnel an unimaginable volume of water toward the deepest parts of the basin. The stage was set not just for a crisis of desiccation, but for a flood. When a sea changes shape, life feels it long before the rocks do. Even before the basin dropped into those strange patchwork levels, things would have been going wrong inside the water itself. The Mediterranean of the Messinian wasn't a calm blue bowl one day, and a salt desert the next. It would have stepped through a long, uneasy in-between. Start with the salt. Modern marine life is tuned very precisely to the salinity of the open ocean. Most organisms can handle small shifts, a little fresher near river mouths, a little saltier in restricted bays. But as evaporation began to dominate inflow, the Mediterranean would have started to drift beyond what many species could tolerate. It doesn't happen all at once. First, subtle stress. Plankton that once bloomed every year start to thin out. Shell-forming organisms, sensitive to changes in water chemistry, struggle to build their skeletons. Fish that depend on those food webs begin to fail in certain regions, then disappear entirely from others. As the basin shoals and divides, some areas might remain relatively normal for a time, fed by whatever water can still slip in through narrow gateways, or by deep circulation that keeps salinity in check. Other regions, more isolated, would cross unseen thresholds. A little more salt, a little more heat, and suddenly whole communities collapse. Coral-like organisms bleach and die. Seagrasses retreat from shallower shelves that swing between too hot and too briny. Animals that can move. Those that cannot either adapt, if they have the genetic room to maneuver, or vanish. Yet even in a collapsing sea, life rarely disappears uniformly. It retreats into corners. Biologists have a word for those corners: refugia. Little pockets where, for one reason or another, conditions remain just good enough. In a drawn-down Mediterranean, refugia might have formed in several ways. Some would be deep. If parts of the central basins remained flooded to great depths, insulated from the worst surface evaporation by density stratification, they could have hosted more stable, slightly less saline waters near the bottom. Currents hugging the sill at Gibraltar or other connections might have slipped under dense brines, bringing in fresher, cooler water that pooled in quiet depressions. In those dim, hushed depths, cold-adapted species might have endured long after their relatives on shallower margins gave up. Other refuges might have been at the edges. Imagine marginal lagoons clinging to the foot of retreating cliffs. As the main water level fell, isolated embayments would be cut off, forming brackish lakes where river water and groundwater could dilute the salt. These would be unstable places, subject to sudden concentration during droughts, sudden freshening during floods. But in that instability, some species might find windows of survival. Estuary-tolerant fish, hardy invertebrates, microbial mats edging the shorelines, turning the fluctuating chemistry into slow, layered films of life. Then there are the spillovers. Even if Gibraltar was mostly closed, it may not have been perfectly sealed for the entire crisis. Models and geological hints suggest intermittent connections, pulses of Atlantic water slipping in during high stands, storms, or small tectonic adjustments. Those pulses would have been like brief breaths in a suffocating room. Near the western entrance, in channels and sills that occasionally felt the tug of the open ocean, ecosystems may have flickered between two states: stressed, hyperevaporitic basins when the door was mostly shut, and short rejuvenations when cooler, less salty water spilled over. Species with broad tolerances and flexible life cycles could have ridden those oscillations, reproducing during the better intervals and hanging on through the bad ones, their lineages threaded through time by narrow recurring windows of habitability. As the basin broke into subseas at different levels, the routes animals used to move would have twisted with it. Wide, continuous coastal shelves that once let organisms spread along the margin would have fragmented. Where there had been gently sloping shorelines, there might now be steep escarpments descending toward distant brine lakes. The highways for coastal fish, invertebrates, and even shoreline plants would narrow to thin corridors around still wet perimeters. Migratory patterns would warp. Some species that had once crossed between the Atlantic and the Mediterranean might find the path abruptly hostile, too salty, too shallow, or blocked entirely. Others, particularly those adapted to marginal variable conditions, the kinds of organisms you find today in estuaries and salt marshes, could discover new opportunities along the freshly exposed coasts. It's easy to forget that as water retreated, it did not simply leave emptiness. It uncovered wet ground, seepage zones, and ephemeral ponds. For birds especially, this shifting mosaic could have been a mixed blessing. Certain flight paths might become harder as large open water bodies vanished. Others could be eased by new resting spots and feeding grounds on exposed mudflats and nascent salt marshes at the fringes of the remaining lakes. For marine mammals, though, the story likely grew harsher with time. Creatures that needed deep, open water and reliable fish stocks would have found the basin less and less welcoming. Some might shift their ranges outward, hugging the Atlantic side. Others, if they tried to follow retreating waters into over-deepened pockets, would be funneling into ecological dead ends, small, stressed basins with little capacity to support large, energy-hungry bodies. As the sea surface fell, the air above it changed too. A wide, warm body of water is an engine for humidity. It feeds clouds, smooths temperature swings, softens nearby climates. Take that away, or shrink it to smaller, hotter lakes, and the surrounding lands begin to dry. With the Mediterranean surface pulled down, large areas that had once been moderated by sea breezes would now overlook rock and salt. The air crossing that new interior would pick up dust, not moisture. Winds funneling down canyons might lift fine particles from desiccated flats, carrying them onto the surrounding plateaus. Over time, those dust plumes could alter nearby ecosystems. Thin-soiled slopes around the basin might struggle to hold vegetation in the face of more intense, drier winds. Yet dust is also a fertilizer. Iron, phosphorus, and other nutrients embedded in those grains might land hundreds of kilometers away, falling on distant seas or upland forests, subtly nudging their productivity. Salt would join the journey. On dry days, crystals at the surface of evaporate flats can sublimate and fragment, releasing tiny halite particles. Sea breeze analogues blowing inland from the shrunken lakes could deposit that salt on nearby soils and plants, stressing some communities, favouring others that can cope with saline spray. Over centuries, entire belts of vegetation could resort themselves, tracking the gradients of dust, salt and changing rainfall. Humidity patterns would shift as well. With less open water to evaporate from, the regional hydrological cycle around the basin might tilt toward more extreme swings. Hot, clear days with very dry air, punctuated by rare, violent storms when moist air masses from elsewhere crash into the heat rising from the low basin floor. Those sudden downpours would carve gullies into the exposed slopes, but they'd also pulse nutrients and sediments into the remaining lakes, seeding short-lived blooms of algae and bacteria in otherwise quiet waters. What does the fossil record say about all this? It is, frustratingly, both eloquent and incomplete. In some Messinian deposits, especially on the margins, we see assemblages that look like stressed communities, species that tolerate wide salinity ranges, brackish water mollusks, microfossils typical of lagoons rather than open seas. Layers of gypsum and halite are interbedded with thin bands rich in organic material, suggesting cycles, episodes where hypersaline conditions gave way briefly to more life-friendly waters before concentrating again. In a few places there are indications that deep marine conditions persisted at some times, somewhere in the basin. Certain microfossil assemblages and geochemical signatures hint at water columns that, while salty and strange, still stratified like oceans do, with oxygen-poor bottom waters and more oxygenated, potentially livable layers above. But gaps are everywhere. Many of the environments that would have been most interesting biologically, temporary lakes at the foot of retreating cliffs, short-lived estuaries along retreating shorelines, microbial mats on salt flats periodically flooded and dried, are exactly the kinds of deposits least likely to survive in a clear, continuous record. They are prone to erosion, to later overprinting by younger seas, to being buried under thick blankets of salt. So what we see is a patchwork. Hints of lagoons here, traces of deep water there, thick evaporates telling us that at least at some times and places, evaporation massively outpaced replenishment. We can say, with some confidence, that ecosystems around and within the Mediterranean were repeatedly stressed, reorganized, and in some regions dramatically simplified. We can't yet reconstruct every refuge, every narrow corridor of survival that threaded through the crisis. Still, it's possible to stand back and imagine the basin near the height of its transformation, not as a lifeless void, but as a world of edges. Edges between water and air, where new shorelines cut across old seafloors. Edges between tolerable and lethal salinity, sometimes separated by only a few meters of depth. Edges between moist, moderated climates and the harsher, dustier belts just beyond the reach of the shrunken lakes. Along those boundaries, life would gather. In seep-fed pools at the base of canyon walls, reeds and rushes might fringe brackish water, buzzing with insects, visited by birds on restless journeys. On the margins of hypersaline pans, mats of bacteria and algae could lay down thin, rubbery carpets of colour under a glaring sun. In the deeper, cooler refuges, unseen in the murk, small fish and invertebrates might circle on, heirs to lineages that had learned to endure long droughts of the sea. For them, the Messinian crisis was not a geological curiosity. It was the fabric of their world stretched, torn, and slowly resewn. And while they clung to those shifting edges, another threshold was being prepared elsewhere. Far to the west, beyond the salt flats and collapsing margins, a narrow sill of rock and sediment still held back the full weight of the Atlantic. The basin had emptied, at least partly. The ecosystems had retreated to their corners. The air above had changed. All that remained was for the gate to yield. The Mediterranean has always lived on a kind of allowance. It loses water to the sky faster than rivers, and rain can replace it. Day after day, year after year, sunlight lifts molecules off its surface and carries them away. Left to itself, the basin would slowly shrink and concentrate, just as it did in the Messinian. What stops that from happening today is not some inherent stability of the sea, but a narrow arrangement of rock and depth at its western edge. The Strait of Gibraltar is not just scenery on a map. It is a valve. Stand it up in your mind like a doorway between two rooms. On one side, the Atlantic, huge, deep, with water that is, on average, slightly cooler and slightly fresher. On the other, the Mediterranean, smaller, warmer, saltier, and constantly evaporating. Because Mediterranean surface water becomes saltier, it also becomes denser. It wants to sink. Because it is losing volume to evaporation, it is also very gently drawing water in. The result is a strange, quiet conveyor flowing through that rocky gap. At the surface, there's a net flow from the Atlantic into the Mediterranean. Fresher water slides eastward over the sill like a river running into a thirsty lake. At depth, denser, saltier, Mediterranean water creeps back out, spilling westward along the bottom, descending the Atlantic slope like a slow underwater waterfall. Two layers, sliding past each other through a channel barely 300 meters deep at its shallowest point today. A fragile balance maintained by a few hundred meters of relief on the seafloor and the relentless arithmetic of evaporation and inflow. Change the shape of that doorway, and the whole system changes with it. Over millions of years, plates grind and flex. The African plate pushes northward into Eurasia. Pieces of crust crumple, sag and shear. At the same time, rivers chew at their valleys, deltas grow and slump, submarine fans pour sediment into every low spot they can reach. Seaways are not static corridors, they are works in progress. Imagine the region around Gibraltar not as a fixed gap, but as a geologically restless hinge. Uplift on one side can raise the sill, the shallowest part of the passage, by tens or hundreds of meters. Subsidence on another can deepen it. Sediment washed in from nearby rivers can pile up, narrowing the effective cross-section, then be swept away by stronger currents during storms or sea level highs. Even modest changes matter. Make the sill a little shallower, and you restrict the area through which those two layers can exchange. The surface inflow weakens, the deep outflow thins. Evaporation keeps pulling, but now the pathway for compensation is cramped. The Mediterranean begins to slip further out of equilibrium, slightly lower, slightly saltier, slightly more dependent on that struggling inflow. Push things further, raise the sill more, or clog it with sediment, and you edge toward thresholds. There's no need for a giant sudden mountain to rise in the middle of the strait. A sequence of small uplifts and collapses, tilted blocks, slow warping of the crust, combined with the ceaseless delivery of mud and sand, can repeatedly reshape how easily water passes between basins. In some models of the Messinian, the change from a healthy two-layer exchange to a choked, precarious trickle happens when depths cross certain critical values, when the sill becomes too shallow to support stable separated flows. Once that happens, the physics of exchange rearrange themselves. Under modern conditions, the Mediterranean's outflow at depth is dense enough to hug the bottom and exit cleanly beneath the incoming surface water. The two layers remain mostly distinct as they cross the sill. That separation keeps the conveyor running efficiently, but if you raise the sill, the deeper layer is forced upward. It may be squeezed into a thinner band, forced into shallower pressures and temperatures, or even partially mixed with the incoming water. Turbulence increases. The sharp interface between inflow and outflow blurs. At a certain point, the system can flip from a clean two-layer exchange to something messier. Intermittent surges, brief reversals, or near-complete shutdowns of deep outflow. The Mediterranean then becomes more and more of a cul-de-sac. Water goes in, but it doesn't come out in the same organized way. Salt accumulates, levels fall. Yet Gibraltar was not the only opening in this ancient plumbing. Before the modern strait settled into its current form, water could also pass between the Atlantic and the Mediterranean through other corridors, shallower, more complex pathways threading through what are now southern Spain and northern Morocco. Geologists give them names: the Betic corridors to the north, through the mountains of southern Iberia, the Rift corridors to the south, across the rising highlands of northern Africa. Picture a landscape less consolidated than today. Instead of one clear throat at Gibraltar, there's a lace of straits and seaways, island-choked passages and low saddles between basins. During some periods, water likely flowed in through multiple gateways at once, distributing the Atlantic connection across a broad zone. As tectonics marched on, those corridors narrowed and lifted. The Betic routes, high in what would become the Sierra Nevada and surrounding ranges, gradually rose above sea level. What had once been marine channels turned into shallow arms of the sea, then estuaries, then river valleys. The rift corridors to the south did something similar, buckling upward as Africa pressed north. Each closure removed a piece of the inflow puzzle. By the time the Messinian crisis loomed, it's plausible that the Mediterranean was relying mostly, or even entirely, on the Gibraltar region for its deep connection to the Atlantic. The other valves had been shut one by the slow hand of tectonics and sedimentation. A system that had once been robust, able to lose one gateway and lean on another, had become brittle. A single narrow throat now carried almost all the responsibility for keeping an entire inland sea from drifting into desiccation. In that setting, small becomes relative. A change of 100 metres in sill depth across a channel only a few kilometres wide might not seem dramatic on the scale of continents, but for a body of water whose level and salt budget depends sensitively on the ease of through-flow, it can be the difference between a stable, well-flushed basin and one that slowly spirals inward. Hydrologists think in terms of budgets and thresholds. How much water comes in? How much goes out? How much is lost to evaporation? How much is gained from rivers and rain? If the sum of all these terms keeps basin level within a certain range, you get a sea that merely breathes with climate. Levels rise a bit in wetter times, fall a bit in drier times, but never tip into catastrophe. Narrow the gateways, and that comfortable buffer shrinks. Inflow becomes more sensitive to storms, tides, and subtle changes in density contrast between the Atlantic and the Mediterranean. There may be long quiet spells where little water passes the sill at all, punctuated by episodes when unusual conditions, an especially high Atlantic level, or a shift in winds and currents, push a slug of water through. From inside the basin, these pulses would feel like erratic gifts, a year or a century of relative relief, then a return to relentless concentration. There is a kind of irony here. The more the Mediterranean evaporates and becomes salty, the denser its waters become, and in principle, the more eager they are to sink and flow back out into the Atlantic. But if the gateway controlling that escape route has become too shallow, too narrow, too roughened by sediment and tectonic scars that eagerness is trapped, density wants to drive circulation one way, topography refuses. In this sense, the Messinian Mediterranean may have been living in a state of suppressed motion, its internal physics primed for exchange, its surroundings conspiring to prevent it. What finally pushes such a system over the edge is unlikely to be a single dramatic gesture. Instead, it may be the accumulation of many quiet shifts, millimetres of uplift each year at a critical sill, centimetres of sediment added by each flood season, variations in global sea level riding the rhythm of ice ages, raising and lowering the base level against which all these channels are cut. Raise global sea level, and the Atlantic presses a little higher against the gates. Lower it, and the pressure drops. In some scenarios, a fall in global sea level might help isolate the Mediterranean, amplifying the effects of a shallow sill. In others, a subsequent rise could bring the Atlantic's reach back up to a level where a weakened barrier fails. Throughout, erosion is at work in the other direction. Where water does manage to cross a sill, it scratches at the rock, deepening and widening the gap grain by grain. Under the right conditions, that feedback can become runaway. A slightly deeper notch allows more flow enhances erosion deepens the notch further. The plumbing around Gibraltar, the Betics and the Riff was poised between these forces, uplift lifting the thresholds, sediment trying to fill them, water trying to cut them down. For a long stretch of the Messinian, uplift and infill seem to have held the upper hand. The gates tightened. The Mediterranean slipped basin by basin toward its strange desiccated state. But fragility cuts both ways. A system so sensitive to small changes can lock into crisis. It can also unlock spectacularly when conditions tip back. At some point near the end of the Messinian, something in that western hinge shifted. Perhaps tectonic subsidence lowered part of the sill. Perhaps erosion, working quietly through a narrow, still wet channel, finally deepened a critical point. Perhaps global sea level rose just enough to let the Atlantic lean harder against a weakened barrier. Whatever the exact combination, the effect would have been the same. A subtle reconfiguration of seafloor and shoreline that turned a throttled valve into a failing dam. The Mediterranean had spent hundreds of thousands of years evaporating behind a misaligned doorway. Its salt beds lay ready, its canyons cut, its margins collapsed and rearranged. Far to the west, the gate that had nearly closed was about to swing the other way, not to its old, gentle balance, but to something far more violent. When that happened, water would not simply resume its quiet two-layer dance. It would fall, it would accelerate, it would carve. The fragile plumbing of oceans, after holding back a sea, was about to show what happens when a threshold finally gives way. The first sign would not have felt like the end of a world. It might have begun as a change in the sound of distant water, a muted, ceaseless murmur somewhere to the west, beyond the horizon. The kind of background noise you notice only when the wind drops and the air goes very still. On the Atlantic side of that failing barrier, the story was simple. The ocean was there, as it had always been, deep, heavy, pressing against the western slopes of the rising mountains and sills that framed the ancient Gibraltar region. On the Mediterranean side, the story was anything but simple. What lay beyond the crumbling thresholds was not the familiar blue expanse we know today, but a stepped, fractured landscape. Deep basins choked with air and dust, vast salt plains glittering under a hard sun, lakes stranded far below global sea level, fed by shrunken rivers that tumble down over 1,000-metre escarpments. The difference in height between the Atlantic and the deepest parts of this desiccated Mediterranean may have been on the order of 1 or 2 kilometres. In some reconstructions, the Atlantic shoreline stood hundreds of metres above even the highest surviving Messinian lake surfaces. A wall of potential energy, written not in rock, but in water. For a long time, that energy stayed locked up behind the worn, uplifted, sediment-stuffed ridges of the Beatix, the Riff, and the Gibraltar Sill. Narrow channels carried only a trickle. The imbalance between a full ocean and an emptied basin was real, but it was kept at bay by topography that for the moment still held. Then, near the dawn of the Pliocene, something crossed a threshold. Geologists call the moment that followed the Zanclean flood. Zanclean for the earlier stage of the Pliocene epoch. Flood, because no gentler word quite fits the scale of what some models suggest. In its simplest outline, the mechanism is straightforward. Imagine the Atlantic like a reservoir, the Mediterranean like a dry quarry far below, and the Gibraltar region as the dam between them. At some point, either because global sea level rose, or a portion of the sill subsided, or an existing narrow channel was quietly deepened by long-term erosion, Atlantic water found a continuous, low path across that barrier. The first trickle crept over the sill and began to descend the far side. Once that happened, physics took over. Water flowing downhill accelerates. As it accelerates, it gains the power to move sediment and gnaw at rock. The faster it moves, the more effectively it cuts. Cut a little deeper into the sill, and you lower the spillway. Lower the spillway, and suddenly the height difference between the Atlantic and the Mediterranean increases. More height means more potential energy. More energy means faster flow. Faster flow means more erosion. More erosion deepens the channel, and the cycle tightens on itself. This is what geomorphologists call a self-amplifying, or positive, feedback. A narrow, shallow breach can sharpen into a canyon. A modest waterfall can become a plunging cataract. A localized leak can, under the right geometry, reorganize into a runaway drainage. If you scale that process up to fit a whole ocean pouring into an underfilled basin, you arrive at the more dramatic visions of the Zanclean flood. In some numerical models, once a through flow is established, the Atlantic begins to rush eastward through a deepening gorge at rates that are difficult to grasp. Waterfalls hundreds of meters high cascading into a spreading lake. A jet of incoming flow scouring a trench that races east, its head cutting across the floor of what is now the Alboran Sea, then deeper into the main Mediterranean basin. Depending on the assumptions you feed into those models, the exact height difference, the resistance of the rocks, the details of global sea level, estimates for how long it took to refill the Mediterranean range widely. Some reconstructions suggest a relatively gentle scenario, decades to thousands of years of intense inflow, a drawn-out reconnection rather than a single short-lived catastrophe. Others, especially those that treat the process as a true megaflood, converge on startlingly short timescales. Months, a year or two. In these versions, the Mediterranean might have risen tens of meters per day in its deepest parts, shorelines racing upslope faster than a person could walk. Most researchers agree on the broad outline. There was a restricted gateway, there was a deep underfilled basin, and there was a rapid transition to a refilled sea at the start of the Zanclean. The exact pace and violence of that transition, however, remain matters of debate, constrained by imperfect data and models that simplify a very complex landscape. Still, even if we take the calmer end of the spectrum, we're dealing with a refilling event that was rapid on geological timescales, not millions of years, not even hundreds of thousands, something closer to the span of civilizations, or less. To imagine it from within the basin, forget the view from space and drop yourself into a low valley floor, somewhere along what had once been the margin of the old Messinian Sea. At first the change might have been subtle. The dry heat that had ruled for ages softens slightly. Humidity edges up. Morning mists cling a little longer in the hollows. Rumours travel from the west. Somewhere, beyond the broken escarpments, a new river has appeared. Not a normal river that you can ford with a careful step, but a wide, relentless sheet of water, too deep to cross, too loud to ignore. Days pass. The river swells. What had been a canyon with sheer, silent walls now carries a restless sound that never fully dies away. You might notice the line of dampness creeping higher on the rock, little by little at first, then faster. At a certain point, the language of rivers no longer applies. The incoming flow would not have been a gentle current with polite banks. It would have been a supercharged conveyor of Atlantic water plunging into air, generating spray and turbulence, rolling boulders, ripping apart any unconsolidated sediments that had accumulated on the slopes of the sill. Where it hit the floor of the basin, it would have fanned out into a roiling, expanding lake. That lake would have climbed day by day, carrying its shorelines upslope, swallowing salt flats, escarpment bases, collapsed margin blocks. Every rise in water level would have increased the pressure at the base of the inflow channel, encouraging more erosion there. The gorge back at the gateway would have deepened, widening until it matched the flow demanded by the growing head difference. In this way, the erosion at the sill and the rise of the basin were linked parts of a single process, each amplifying the other until a new equilibrium was reached. A Mediterranean refilled enough that the height difference between it and the Atlantic shrank back to the modest values we see today. At that point, inflow would have eased. The roaring cascade would have settled into something more like the modern two-layer exchange, a surface inflow, a deep outflow, quietly shuttling salts and heat instead of excavating rock. We do not have eyewitness accounts. What we have are indirect traces, deep erosional features near Gibraltar that some interpret as the scars of catastrophic incision, peculiar sediment layers that could be the deposits of huge, short-lived currents, the abrupt shift in microfossils and geochemical signatures at the Messinian Zanclean boundary that testifies to an environment restored from hypersaline extremes to open marine conditions. On one side of that boundary in the cores, you see the fingerprints of an almost alien inland sea. Thick salt layers, disturbed by slumps and collapse, signs of extreme concentration and fluctuating water levels. On the other side, you see the return of normal marine life, plankton communities typical of open ocean conditions, chemistry that matches what you'd expect from a well-connected, oxygenated basin. The transition between these two states looks sharp in many records, sharper than you'd expect if the refilling had been slow and incremental over tens of thousands of years. That sharpness is one of the clues that pushes some scientists toward the faster, more dramatic Zanclean flood scenarios. Still, there is room for nuance. Even in a weeks to years megaflood model, different parts of the basin would have responded at different paces. The deepest central depressions would have seen levels climb rapidly. Marginal basins might have filled more gradually, as the rising sea invaded over sills and through relict river valleys. Local topography would have controlled where waterfalls formed, where quiet embayments developed, where old Messinian canyons turned into new submarine slopes. From a quiet vantage point high on one of the former basin margins, the experience might not have been one of apocalyptic chaos, but of steady, relentless change. Each morning, the line between land and water is a little higher. Each week familiar landmarks are gone. A salt pan drowned, a cliff base transformed into a wave-cut shore, a distant plume of spray at the main cataract slowly shortened as the head difference decreased. Night after night the background roar softens by imperceptible degrees, as the breach at Gibraltar widens, deepens, and then finally relaxes into something more stable. By the time the system settles, the map of the region has been rewritten. Where there had been a mosaic of basins and salt flats, there is once again a connected sea. The deep canyons carved by Messinian rivers are drowned, turned into the submerged valleys and continental slopes that modern ships now cross without ever seeing. The Gibraltar region holds, not as a dry dam, but as a narrow throat where two great water masses meet and trade. The same basic configuration as today, but shaped, perhaps abruptly, by that moment of failure and reorder. What is widely accepted is this. At the start of the Zanclean, the Mediterranean shifted from an isolated evaporitic basin back to an open marine sea, and it did so quickly on geological timescales. The Atlantic connection at the western margin was the critical control, and its reopening involved substantial erosion and restructuring of the seafloor. What is inferred, modelled and debated is the exact choreography of that reopening. How narrow the first breach was, how tall the initial waterfall might have been, whether the refilling was an intense short-lived megaflood or a somewhat more leisurely, but still rapid, reconnection stretched out over longer human timescales. Either way, the Zanclean flood marks the moment the balance flipped. For hundreds of thousands of years, uplift and sediment had conspired to choke the gateways, favouring evaporation over inflow, pushing the Mediterranean toward absence. Then, in what may have been the span of a handful of human generations, or fewer, the same landscape allowed water to race back in, erasing an inland desert sea and restoring blue where white salt and brown rock had ruled. The valve at the western edge had stuck. Then it had snapped open. What came next was the long settling of the new Mediterranean, its currents, its climates, its coasts, under the imprint of that sudden return. To understand whether the Mediterranean could really have refilled in a matter of weeks, we have to step back from the roar and mist, and look at the problem the way a hydrologist or a physicist would. Strip away the drama for a moment, and the question becomes almost childishly simple. How big was the empty space? How fast could water flow into it? And how high did that water have to climb before its rage began to calm? Those three things, basin volume, inflow rate, and the height of the gateway sill, are the quiet controls behind every spectacular megaflood. Start with the basin. Today's Mediterranean holds on the order of a few million cubic kilometres of water. During the Messinian Salinity Crisis, it probably never became a completely dry hole from Gibraltar to the Levant, but much of its volume was gone. Deep central depressions might have been more than a kilometre below global sea level. Peripheral shelves might have held briny lakes or patchwork seas, their surfaces stepped at different elevations. So when scientists talk about refilling the Mediterranean, they're really talking about adding back some large fraction of that missing volume. Not all of it, in one go, but enough to bring the basin back to something like modern sea level, or at least to flood most of the deep depressions. If you know, even approximately, how much water you need, the next question is, what kind of hose are you using? That hose is the Gibraltar Gateway. Every drop of Atlantic water entering the Mediterranean at the start of the Zanclean had to squeeze through a corridor that, at first, might have been surprisingly narrow and shallow. The sill, the shallowest part of the barrier, controlled the initial head difference, the height between ocean level and the top of the spillway. A high sill means a small initial overflow, a tentative seep. A slightly lower sill or a pre-existing channel cut just a bit deeper can turn that seep into a chute. Once the water overtops the sill and begins to tear at the far side, two things matter for the inflow rate: the slope and the shape of the channel. Steeper slopes make water accelerate. Narrow, confined passages focus the flow. Together they define the discharge, the volume of water passing any given point per second. You can think of discharge like the strength of the flood. A garden hose has a tiny discharge. A large river at flood stage might move thousands of cubic meters per second. The Amazon, in the wet season, can exceed 200,000. The Zanclean flood, in some models, reaches into figures that are difficult to say out loud without pausing. To get those numbers, scientists use tools borrowed from both rivers and glaciers. They map the shapes of buried channels around Gibraltar using seismic profiles, acoustic scans of the seafloor and the rock beneath. They look for V-shaped incisions that slice deeply into older layers, for over-deepened troughs and abrupt nick points that suggest past waterfalls. From those geometries, the width and depth of the inferred canyon, the slope of the floor from the sill down into the basin, they can plug values into hydraulic equations that describe how water flows in open channels. The basic idea is straightforward. For a given slope and roughness, there is a relationship between flow depth, velocity, and discharge. If a channel is very deep and wide, and it shows signs of having been carved rapidly, then the flows that made it must have been immense. You can then play a kind of inverse game. Ask, what discharge would be required to produce this erosion, given this rock type, in a very short time? Or, if this was the maximum discharge, how long would it have taken to move enough water to fill some fraction of the Mediterranean's missing volume? Depending on the assumptions, how resistant the rocks were, how much of the channel we're actually seeing, how dry the basin really was, those back calculations produce a spread of scenarios. On the more restrained end, you get what might be called the fast but not apocalyptic models. In these, the Gibraltar Channel carries discharges comparable to, or perhaps an order of magnitude larger than, the largest modern rivers and known glacial outburst floods. The Mediterranean refills over years to decades. The flow is still ferocious, the erosion still deep, but the process has time to step, pause, and adjust. On the extreme end, you find the true megaflood visions. Here, discharges climb into the tens of millions of cubic meters per second, rivaling or exceeding the largest outburst floods known from the geological record, such as those that drained the ice-dammed lakes of North America at the end of the last glaciation. For comparison, think of the Missoula floods in the Pacific Northwest of the United States. Those were cataclysmic releases of glacial meltwater, with estimated peak discharges on the order of 10 million cubic meters per second, carving the channeled scablands, ripping away hundreds of meters of rock and soil, leaving behind streamlined hills and giant ripples taller than houses. Even those floods, by some estimates, lasted days to weeks at a time and recurred many times as ice dams failed and reformed. Some Zanclean flood models suggest similar or even larger discharges pouring into the Mediterranean basin, not from an ice lake, but from the open Atlantic. With flows like that, you do not need centuries. If the basin were deeply underfilled, say by several hundred meters, those peak discharges could, in principle, raise water levels in the deepest parts by tens of meters per day. Under the most aggressive assumptions, you could go from a largely empty central basin to something approaching modern depths in a matter of months, or, in the most compact reconstructions, in somewhere on the order of a few tens of weeks. That is where the refilled in weeks headlines come from, but every one of those numbers hides uncertainties. We do not know, with precision, how empty the Mediterranean really was just before the flood. Some models favour a nearly dry central basin, its floor littered with salt and dust. Others prefer a more modest drawdown, with deep hypersaline lakes cushioning the worst of the relief. Lower initial dry volume means less water needed to refill, and therefore shorter timescales for any given inflow rate. A truly gasping, empty basin demands more water and time. We also do not know whether the process was a single, uninterrupted torrent, or a series of pulses. The Gibraltar region may have failed in stages. An initial breach might have formed, cutting a canyon and sending a first great wave of water eastward. That pulse could have temporarily narrowed the height difference between the Atlantic and the Mediterranean, slowing the flow, allowing some partial equilibrium to develop. Later tectonic adjustments, continued subsidence, or even simple erosion lowering the sill further, could then have triggered new accelerations, new pulses, new steps in the rise of Mediterranean level. In that sense, the Zanclean event might have resembled the glacial outburst floods of the Pleistocene, not just in magnitude but in rhythm. Catastrophic releases separated by quieter intervals of relative stability. From the perspective of the rocks, both pictures, a single immense pulse, or several large but smaller surges, can leave similar scars. Deeply incised gateways, abruptly truncated sedimentary sequences, sharp transitions in microfossils and chemistry. The boundary between Messinian and Zanclean deposits in many cores certainly looks abrupt. The return of open marine conditions seems to happen over a very thin interval, perhaps too thin to comfortably host tens of thousands of years. But thin on a drill core does not neatly distinguish between a decade and a century, or between a single continuous megaflood and a tightly clustered sequence of major floods, and so the debate lives in that gap. Advocates of the fastest scenarios point to the sharpness of the sedimentary transition, the depth and geometry of the inferred Gibraltar Canyon, and the physics of self-accelerating spillways. If you take a large head difference, a vulnerable sill, and reasonably erodible rocks, they argue, it is very hard to avoid a runaway incision. Once you start, the system quickly organizes itself into a maxed-out flood. limited mainly by the capacity of the channel and the overall pressure difference between ocean and basin. Under those circumstances, refill times of months to a few years feel not only possible but likely. Others are more cautious. They point out that the subsurface images we have of the Gibraltar region are imperfect, that erosion there has been overprinted by later processes, and that our hydraulic equations were mostly calibrated on rivers and smaller floods, not on ocean-scale events. Rock strength in the sill might have been higher than assumed. The gateway may have had multiple parallel channels, each sharing the load. Parts of the basin may have already been partly flooded before the main connection, reducing the effective height difference and muting the extremes. In their view, refill over several decades to perhaps a few centuries is more comfortable, still brutally fast in geological terms, and still dramatic on human ones, but less like a single roaring disaster, and more like a series of sustained, violent surges. Both sides agree on something important. Whatever the exact number of days or years, the Zanclean refilling was fast enough that normal, slow sedimentation could not keep up. It was a threshold event, not a gradual slide. A system poised between two stable states, isolated evaporitic basin and open marine sea, that flipped from one to the other when the Western Gateway crossed a critical depth. On a human timescale that still leaves a wide range of possible experiences, in the most extreme models, you could stand on a former basin margin and watch the shoreline climb tens of meters between one moon and the next, rivers backing up, salt pans drowning, cliffs transforming as waves undercut their bases. In the more moderate ones, the change would unfold across generations. Children would grow up remembering only the advancing sea, the constant, patient rise that turned ancestral lowlands into bays and gulfs. What the evidence cannot yet tell us is which of those worlds was real. We can read the sharpness of the boundary, the shape of buried canyons, the chemistry of ancient waters. We can compare them to other megafloods we know better, glacial lakes bursting, ice dams ripping apart, Mars valleys carved by sudden flows, and borrow analogies and equations. But the exact tempo of the Zanclean flood remains just beyond our direct grasp, living in the space between models and rocks. What we can say is that, whatever its precise choreography, the physics of a megaflood were at work. Potential energy locked in a height difference, a vulnerable sill acting as a valve, positive feedback turning a trickle into a torrent, a basin whose fate could be rewritten, not over the slow grind of millions of years, but within spans of time that, had there been eyes to see, could have watched it happen. When the last of the great surges faded and the Mediterranean approached its new level, the violence subsided into the more familiar, quieter exchanges of tides and currents. The scars of the flood were buried, softened, folded into the everyday life of a sea. Yet beneath the waves, in the shape of the seafloor and the chemistry of its oldest Pliocene sediments, the memory of that brief, furious refilling remains. The debate over whether it took weeks, months, or years will continue, sharpened by new data and better models. But in every version, the message is the same. Large parts of the Earth's surface can, under the right conditions, change not gently but abruptly. What followed, after the water found its new balance, was the long reshaping of coasts, climates, and ecosystems around this restored inland sea. A quieter, slower story, but one still stamped by the echo of that megaflood. When the rush finally eased and the water level stopped chasing the sky, the Mediterranean did something almost shocking, given what had just happened. It calmed down, not all at once, not in every corner, but the era of walls of water and roaring cataracts was over. The basin had crossed its threshold. What came next was the slow work of settling, smoothing, and forgetting. For the land around it, that meant one thing above all: redraw the map. Imagine those great canyons that rivers had cut during the low stand. The Nile, the Rhone, the Ebro, the Po. Each of them had once dropped off the edge of what used to be a coastal plain, and plunged down toward a distant shrunken sea, slicing valleys thousands of meters deep. As the Mediterranean rose, those overdeepened gashes began to flood from the bottom up. The lower reaches of the canyons drowned first, turning into long, narrow inlets. As the water kept climbing, the flooded sections crept upstream, mouth after mouth, bend after bend. What had been a river valley became an estuary, then a bay, then a gently widening shelf. Some of the steepest lower reaches, with their cliffs and hanging tributaries, never got the chance to fill with river mud, They were instantly converted into underwater canyons, submarine extensions of the rivers now hidden beneath a few hundred meters of seawater. If you could drain the modern Mediterranean again, you would still see them. Great gouges cutting into the continental margins, pointing like arrows toward the deep basin. Many of them are the ghosts of Messinian canyons, modified but not erased by the Zanclean flood and everything that followed. On shore, the story was different. River mouths that had once been stranded far from the coast now found the sea pressing in on them. Deltas that had marched out across exposed continental shelves during the low stand were drowned, their tops planed off by waves, their channels reworked into new patterns. The Nile Delta, which today flares out into the southeastern Mediterranean like a green fan, would have had to start again. New distributaries, new sandbars, new wetlands, all built on top of whatever distorted landscape the crisis had left behind. Sediment pathways, the routes by which mud, sand and gravel move from land to ocean, were completely reorganized. During the Messinian drawdown, most of that material had raced downslope, tumbling into the deep basin along gullies and alluvial fans, piling directly onto evaporate plains and exposed bedrock. After reflooding, the new Mediterranean began to behave more like the one we know. Rivers dropped their loads on broad coastal plains and shallow shelves. Finer silts and clays spread out in thin layers over the deeper parts of the basin. Submarine canyons acted like conveyor belts in storms, funneling some of that material downslope, but the frantic direct connection between mountain and abyss was gone. Stability, in sedimentary terms, means that things start to sort themselves by size and by depth. Coarse grains near shore, finer ones far out, the whole pattern breathing gently with each storm, each season. The Mediterranean had regained that breathing. At the western end, the place where everything had once hinged on a single, catastrophic breach, the gateway to the Atlantic was changing character too. During the flood, the flow through the Gibraltar corridor was almost entirely one way. Atlantic water pouring into a deep, underfilled basin, driven by a huge height difference and self-accelerating erosion. Once levels equalized, that height difference collapsed. What remained was something subtler. The Mediterranean basin, sitting under a relatively warm sun and surrounded by arid to semi-arid lands, tends to evaporate more water than it receives from rivers and rain. Left to itself, it is a thirsty sea. To keep from shrinking, it needs a constant top-up from the Atlantic. That needs set up a new, quieter pattern of exchange through Gibraltar, one that, in broad outline, persists today. At the surface, relatively fresh Atlantic water flows into the Mediterranean, a slow, steady current rather than a screaming torrent. Beneath it, denser, saltier Mediterranean water, concentrated by evaporation, spills back out toward the open ocean as an undercurrent. Two layers, sliding past each other in opposite directions through the same narrow gateway. It is an elegant solution to a simple problem: how to keep a semi-enclosed sea from vanishing again, without ever repeating the drama of the Zanclean flood. We cannot say exactly how quickly this two-layer circulation established itself, but as salinities settled toward a new balance and the basin's shape approached its modern outline, the physics more or less demanded it. The reconnected sea also faced a different kind of challenge. During the Messinian crisis, many parts of the basin had turned into hypersaline traps. Water that remained in the deepest depressions was so salty that only the hardiest microbes could tolerate it. At the margins, vast flats of halite and gypsum had grown where shallow brines evaporated under the sun. The flood did not magically dissolve all of that. Even as normal marine water flowed back in at the surface, denser brine would have tended to sit in the lowest hollows, reluctant to mix. In some reconstructions, the early Zanclean Mediterranean is a layered, subtly unstable entity. Fresher water on top, lurking pockets of ancient brine below. Where those old brines met the invading seawater, chemical fronts formed. Salinity gradients, density contrasts, and temperature differences would have driven slow convective overturning. Tongues of dense, salty water creeping along the bottom towards sills, occasional mixing events breaking through and diluting them. Over thousands of years, those hypersaline pockets would have been slowly bled away, ventilated by deep currents and buried under blankets of ordinary marine mud. The evaporate beds themselves, those gigantic salt deposits built during the crisis, did not vanish. They were entombed. Each new flood, each seasonal river plume, added a whisper-thin layer of sediment on top of them. Over millions of years, those whispers became a thick, muffling blanket. Pliocene and quaternary clays, silts, and sands building up in patient succession. Today, those Messinian salts lie hidden beneath hundreds to thousands of meters of younger rock, deforming under their own weight, flowing slowly like cold honey, creating strange domes and ridges in the subsurface that only show up in seismic reflections and drilling reports. The surface of the sea, though, gave little hint of that buried history. From above, the newly refilled Mediterranean would have looked more and more like a normal ocean basin with each passing century. Blue, calm on most days, ruffled by wind, stirred by storms, breathing heat and moisture into the air. That last role, the quiet exchange between sea and sky, may have been one of the most important long-term consequences of the reflooding. A deep, stable body of water acts as a thermal buffer. It absorbs heat in summer, releases it in winter. It evaporates moisture that can feed clouds and rain downwind. It modifies the temperature swings of nearby land, smoothing extremes, softening frosts, taming heat waves. During the Messinian low stand, the absence or drastic reduction of that moderating influence likely shifted regional climate patterns. Large exposed basin floors would have heated quickly under the sun and cooled rapidly at night. The air above them would have been dry and harsh. Winds could have funneled dust and salt across adjacent continents, seeding deserts and changing where rain fell. With the return of a full Mediterranean, that engine flipped. Instead of a giant reflector and dust source, there was now a dark, heat-absorbing surface, evaporating water day and night. Moisture-bearing winds moving eastward from the Atlantic could pick up additional humidity over the sea, then drop it as rain or snow over southern Europe, North Africa's coastal ranges, and the Levant. We cannot trace every storm track of the early Pliocene, but climate models and proxy data both suggest that the re-established Mediterranean helped to stabilize, and in some regions enhance, precipitation patterns compared to the crisis period. Olive groves, oak forests, and grasslands that would one day characterize the Mediterranean climate mosaic had, in a sense, their stage reset. The return of marine conditions also set in motion the slow repopulation of the basin by life. During the Salinity Crisis, many marine species had either retreated to refuges, perhaps pockets of deeper, less salty water, or marginal areas that remained connected to the Atlantic through narrow straits, or gone locally extinct. Once the flood reopened a broad, deep connection, the Mediterranean became, again, a colonization target. Planktonic organisms, whose spores and larvae drift with currents, were among the first to make the crossing. Carried by the incoming surface flow from the Atlantic, microscopic plants and animals began to seed the newly restored water column. Their remains are what give many early Pliocene sediments in the region their distinctive microfossil signature, a sudden appearance of open ocean species where before there had been brine-tolerant specialists or none at all. Following them, in staggered waves, came the larger creatures. Fish populations expanded into the basin, their ranges pushed by shifting temperatures and salinities. Invertebrates, mollusks, echinoderms, crustaceans spread along the shelves and slopes, moving metre by metre, generation by generation, from the Atlantic and from any local refugees that had survived. Benthic communities colonized the soft muds that began to mantle the abyssal plains, while corals and sponges grew on rocky promontories and canyon walls reworked by the flood. In a geological blink, the Mediterranean went from a stressed, partially desiccated marginal basin to a thriving, reasonably well-connected arm of the global ocean. Not an exact mirror of the Atlantic, its semi-enclosed nature and high evaporation would always give it a slightly saltier, slightly more peculiar character, but no longer the strange end-stage environment of the Messinian. From a distance in time, the contrast is almost soothing. On one side of the boundary, we see extremes, dropping sea levels, thickening salt, collapsing ecosystems, dust and glare, and the rattle of desiccation. On the other, we see a sea that has found its level, a coastline that has stopped racing inland, deltas that are content to creep and shift instead of leap and collapse. Waves nibble at headlands, carving coves and archways over tens of thousands of years. Beaches form and vanish with storms and seasons. Rivers meander across their floodplains, shuttling silt to estuaries that breathe with the tide. Above it all, the Mediterranean settles into the background pulse of the planet, its tides tuned to the moon, its long-term rises and falls governed by ice ages and plate motions, not by catastrophic isolation. If you had fallen asleep on the shore a few 100,000 years after the Zanclean flood and woken up today, the scene would feel eerily familiar. A broad, nearly enclosed sea, mountain chains cupping it to north and south, narrow straits at Gibraltar, at the Dardanelles, at Suez, fishing boats rocking gently in harbours, winds carrying the smell of salt and distant rain. The cataclysm that refilled it would be gone, not only from living memory, but from any story that could be told without the patient forensic work of geology. Yet under the waves, buried in salt giants and drowned canyons, the record remains, proof that this quiet sea once vanished, and then, in a geologic instant, came rushing back. The geologists who first suspected something extraordinary had happened here faced a problem. All the action was hidden. The canyons on land, the weird terraces on the continental slopes, the abrupt changes in fossils, those were hints, circumstantial evidence. They suggested that the Mediterranean had gone through something more dramatic than a simple rise and fall. But the real archive of the Messinian Crisis, the thick piles of salt, the strange layered sequences under the deep basin, lay buried beneath kilometres of water and sediment. To read that archive, you have to learn to see through rock. One of the main tools for doing that sounds almost poetic: seismic reflection. In practice, it's pretty simple in concept. You send sound waves down into the earth, controlled, carefully measured pulses, and you listen for the echoes as those waves bounce off different layers in the subsurface. Each rock type reflects sound in its own way, depending on its density and stiffness. Hard limestone, soft mud, dense basalt, and, crucially for our story, low-density salt, all leave different signatures. Map those echoes, slice after slice, and you get a kind of ultrasound of the basin floor. When geophysicists first ran seismic lines across the deep Mediterranean in the mid-20th century, they expected to see a few hundred meters of ordinary marine sediment draped over older rocks. What they found instead was a continuous, brilliantly reflective band extending across vast areas of the basin, in some places flat, in others folded and buckled, but always recognizable. A single, laterally extensive package separating the younger Pliocene and Quaternary muds above from much older Miocene strata below. In some profiles that band was astonishingly thick, 2 kilometers, 3, in a few deeper centers more. These were the salt giants. On seismic records, salt tends to look almost too clean. It transmits sound differently than the rocks around it, often giving rise to sharp contrasts and internal zones that seem nearly transparent. The Mediterranean basin, once thought to be a modest sediment trap, suddenly revealed itself as a place where something had piled up enormous thicknesses of evaporates, salts and sulfates, over a relatively short window of time. Beneath the calm modern surface, seismic sections showed curtains of salt draped over old basin floors, enormous sheets that had later sagged, flowed, and been squeezed by the slow heave of the crust. The physics of such deposits point to one thing: extreme evaporation. You don't get kilometres of gypsum and halite by accident. You need repeated cycles of water flowing in, concentrating under the sun, and leaving its load of dissolved minerals behind as it evaporates, over and over, on a scale that makes modern salt pans look like puddles. Still, seismic images alone can only tell you so much. They show geometry, thickness, continuity, shapes, but not composition in detail. To know exactly what filled that reflective band, you have to go down there and take a piece of it. That is where deep-sea drilling comes in. Starting in the 1970s, international ocean drilling programs sent ships into the Mediterranean armed with long, hollow drills designed to bite into the seafloor and bring back cores, slender cylinders of mud, sand and rock stacked one atop another, each a frozen slice of time. Lower the drill, rotate, cut, pull up a few meters, repeat. Build a vertical timeline, meter by meter, layer by layer. In some locations, those cores punched straight through the post-crisis marine sediments and into the Messinian world. The change was abrupt. Above, soft greenish or grey Pliocene muds full of marine microfossils, tiny shells of foraminifera and coccolithophores that thrive in open ocean conditions. Below, white and cream layers of gypsum, interbedded with thin laminae of fine detritus. In some places, pure halite, rock salt, massive, crystalline. shot through with fluid inclusions and occasional organic smears. These aren't the kind of deposits you get in a normal well-mixed sea. They look more like what forms today in marginal basins that are nearly cut off from the ocean, the Dead Sea, the Persian Gulf during extreme low stands, salt pans along hyper-arid coasts, except scaled up to an entire deep basin. Between the thick primary evaporates at the base and the overlying Pliocene marine muds, some drill sites hit another kind of layer, a transition zone of mixed deposits, thin beds of anhydrite and gypsum alternating with more typical marine clays and marls. Sometimes there are peculiar conglomerates and breccias, broken fragments of older sediments reworked and dumped into the basin, suggesting episodes of rapid erosion and slope failure. In a few cores, there's a sharp boundary, a surface that looks for all the world like a contact between two worlds. Below, desiccation and salt. Above, the quiet rain of normal marine sediment. At that boundary, microfossils tell their own story. The Messinian evaporates contain very few of the usual deep-sea plankton species. Instead, you find assemblages dominated by forms that tolerate high salinity, shallow water, or strong stratification. Dinoflagellate cysts and benthic organisms that can handle stressed conditions. In some intervals, there's almost nothing at all, a biological silence corresponding to periods when salinity may have exceeded the tolerance of most marine life. Then, right above the crisis horizon, the cores suddenly fill with open ocean species again. Planktonic foraminifera and nanofossils characteristic of fully marine waters reappear, often in great abundance. It's as if someone flipped a switch. One moment, a dying stratified basin. The next, a reconnected arm of the global ocean. But as clear as the basic picture might seem, salt crisis, then flood, there's a complicating factor lurking inside those salt giants themselves. Salt moves. Under enough pressure over enough time, evaporate layers behave less like rigid rock and more like a very slow, very dense fluid. That's the realm of salt tectonics. Imagine you have a thick blanket of halite buried under younger, heavier sediments. The salt is less dense than many of the rocks above it. Gravity does what gravity always does when a lighter material is squashed under a heavier one. It tries to invert the situation. The salt begins to flow, creeping away from areas of high pressure, oozing upward where it can, pooling in lows, thinning under highs. It can form domes that punch toward the surface, pillows that lift overlying strata, ridges that snake along the basin floor. In seismic sections of the Mediterranean, the once flat Messinian salt layer is now carved into complex shapes. In some regions it has risen into domes and diapirs. In others, it has evacuated entire areas, leaving depressions that younger sediments have slumped into. Faults bend around it. Overlying layers drape, sag, and break. All of this motion happened long after the crisis itself. Salt tectonics is slow, but not that slow on geological timescales. As the Pliocene and Quaternary sediments piled on, the evaporates responded, reshaping the subsurface landscape. For scientists trying to reconstruct the original Messinian environment, that's a headache. Did a given thick salt package form in place under a particular sub-basin? Or has it flowed there from elsewhere? Are those vertical stacks of evaporates truly recording repeated cycles of drying and refilling in one spot? Or are some of the thickness variations the result of later migration? When you see a gap in the salt, is it original, an area that never dried, or has the salt been squeezed out? To untangle that, researchers have to cross-check everything. They compare seismic interpretations with drill cores. They look at well logs that capture changes in density and acoustic velocity with depth. They map the regional extent of evaporate units, looking for patterns that make geological sense rather than accepting every wrinkle at face value. They study the microfossils above, below, and occasionally within the evaporates to pin down timing. They use magnetostratigraphy, tiny changes in the alignment of magnetic minerals that record Earth's flipping magnetic field, to correlate sections from different parts of the basin. Onshore, they examine Messinian exposures in Sicily, Spain, North Africa, and the eastern Mediterranean margins. There, in uplifted and eroded slices of what used to be continental shelves and basin edges, you can walk through smaller-scale versions of the story. Marginal gypsum beds with desiccation cracks, stromatolitic crusts built by microbial mats along hypersaline shorelines, lagoonal deposits full of species that thrive in highly restricted environments. Put together, These lines of evidence all point toward the same broad conclusion. At the end of the Miocene, the Mediterranean was, at times, severely restricted from the open ocean. Evaporation outpaced inflow on such a scale that vast amounts of dissolved salts were left behind. Water levels dropped dramatically, at least in parts of the basin. Salinities swung from merely high to practically lethal. Life retreated to refugees or adapted to extremes. Sediment transport pathways reorganized. And then, in the early Pliocene, something changed at the gateways, and normal marine conditions returned, abruptly on a geological clock. Yet within that broad framework, many details remain contested and alive. Did the entire deep basin ever stand fully subaerial, a single immense dry hole, or did pockets of deep, dense brine persist in some depressions throughout the crisis? Were the salt giants laid down during one prolonged phase of drawdown, or did the Mediterranean oscillate between different states, partly full, largely empty, flooded, then restricted again, over several 100,000 years? How fast did the Zanclean reflooding really occur? Was it primarily a single catastrophic spill at Gibraltar, or a more complicated sequence of breaches at multiple sills and corridors, each contributing pulses of water at different times? Even the volume of salt itself raises questions. If you add up all the known Messinian evaporates, the amount of salt seems to require an astonishing number of seawater volumes to have passed through the basin and then evaporated away. That, in turn, loops back into debates about global sea level, the capacity of connecting straits, and the feedbacks between regional events and the broader ocean system. New seismic surveys, using higher resolution techniques, keep refining the shapes of the subsurface structures. New cores, drilled in places where older expeditions never reached, reveal unexpected facies. Laminated deep basin gypsum where only muds had been anticipated, or chaotic breccias that hint at sudden collapses of canyon walls during extreme low stands. Each new piece of data has to be slotted into a puzzle whose outline we mostly know, but whose interior picture is still being filled in. In a way, that uncertainty is part of the calm, nighttime fascination of the Messinian story. We are not looking back at a closed case, with every line of evidence perfectly aligned and every question answered. We are watching an investigation in progress, one that uses tools as gentle as microfossil counts and as forceful as high-energy sound waves shot beneath the seafloor. We can say, with considerable confidence, that the Mediterranean once harboured a world of salt giants, that its connection to the Atlantic was throttled enough to let it nearly vanish, and that it then refilled in an event or series of events rapid enough to leave a sharp boundary in the rocks. But the exact choreography, the number of steps, the pauses, the regional variations, remains open, somewhere beneath the quiet waves, in layers not yet drilled, in structures not yet imaged at the right resolution. The next hints are waiting. A different kind of evaporate, a subtly shifted microfossil assemblage, a buried canyon filled with unexpected sediments. For now, we piece together what we can from seismic echoes and slender cores, from outcrops on land and models on computer screens, tracing the ghost of a vanished sea through the stubborn memory of salt. When you step back from all of this, the salt giants, the buried canyons, the seismic echoes, the Messinian crisis stops being just a strange chapter in Mediterranean history and turns into something else, a demonstration. It shows how a system can look calm and inevitable on the surface, while slow pressures are quietly pushing it toward a threshold. For millions of years before the crisis, the Mediterranean had been just another arm of the global ocean. Water flowed in and out, sediments settled, life adapted to a fairly stable range of conditions. If you could walk along its shores in the early late Miocene, nothing would have told you that this sea was uniquely fragile. The basin was deep. The coasts were familiar in their broad outlines. Tides rose and fell, storms came and went. But beneath that apparent stability, a few critical parameters were drifting. The shape of the continents was shifting. Africa was pushing north, narrowing the seaways. The balance between rainfall and evaporation was tilting toward dryness. Tectonics were lifting some sills, subsiding others. Each change was small in human terms, vast in human lifetimes, but modest on geological scales. For a long time, they didn't seem to matter. Then, one day in geological time, they did. The gateways that had once been wide, deep channels became shallow, constricted passages. The ratio of evaporation to inflow crept just far enough that losses exceeded gains. A sea that had functioned as a throughway in the global circulation began to behave more like a trap. Cross a certain line in that kind of system, and you don't get gentle adjustment. You get a flip. The Mediterranean is a clear example of what scientists sometimes call a threshold or tipping element. A system that responds gradually to change for a while, and then, when some combination of conditions is met, reorganizes abruptly into a very different state. During the Messinian, that new state meant salt plains, brine pools, and perhaps a basin that, at its lowest points, was thousands of meters below the world's oceans. Think about how little had to change at the straits to start that cascade. A sill is raised a few dozen meters, sediment slowly clogs a channel. Relative sea levels adjust as ice builds on distant continents. None of those shifts is inherently catastrophic, but together, in just the wrong arrangement, they push the system past its balance point. The Mediterranean doesn't care about our intuitions of what seems too small to matter. It responds to physics, water budgets, salinity, density, pressure. Once evaporation was consistently winning, once inflow couldn't keep up, the path toward extreme drawdown became almost unavoidable. That's one lesson of this vanished sea. Connected basins depend on narrow gateways more than they appear to. You can have millions of cubic kilometers of water and still be hostage to a strait only a few dozen kilometers wide and a few hundred meters deep. Close that gateway just enough, under the right climate, and you transform an oceanic sea into something more like a gigantic dying lake. The Messinian story also underscores how tightly climate and circulation are linked. When the Mediterranean was cut off, it wasn't just a local curiosity. It effectively dropped out of the global conveyor system for a while. The salt that had been distributed gradually through evaporation and export became locked into the basin as rock. That changes the salinity balance of the surrounding oceans. It may have altered density contrasts that help drive large-scale currents. Some researchers have suggested that the crisis left a fingerprint on global climate, subtle but real, by removing a major site of evaporative cooling and heat exchange. The refilling, the Zanclean flood, reversed that in a burst. Imagine what it means to suddenly reconnect a deeply desiccated basin to the Atlantic. Vast amounts of relatively fresh water pour in. Dense brines at the bottom are diluted, mixed, and eventually exported back into the world ocean. Salt that was effectively quarantined in a closed system is once again part of the global budget. Even if the reflooding took years rather than days, in geological terms it was an instant. A rearrangement of coastlines, salinity gradients, and circulation patterns compressed into a tiny sliver of time. When scientists try to make sense of past climates, why ice sheets advanced or retreated, why monsoons strengthened or weakened, they have to account for events like this. They are the hidden switches and levers behind some of the broader patterns in the record. The Mediterranean, in this view, is not just scenery. It's a sensitive component of the climate machine, capable of flipping between states when tectonics and climate nudge it to the edge. There's another layer to the lesson carved into the stone itself. Landscapes remember water. During the Messinian drawdown, rivers responded as they always do when a base level drops. They cut downward, fast. The Nile, the Rhone, the Ebro, and many smaller rivers suddenly plunged across newly exposed shelves toward a base level that might have been more than a kilometre below the old shoreline. They incised enormous canyons, some of which we can still trace today beneath the modern seafloor. Those buried gorges are fossils of an absence, of a time when the sea wasn't there to catch the rivers. Along the margins, wave-cut terraces, deltas stranded far below present sea level, and odd benches on the slopes of the basin walls all carry the imprint of vanished shorelines. Each notch and platform is a snapshot of a temporary equilibrium between water and rock. Then the flood came, and the script reversed. Valleys that had been carved deeply were suddenly overwhelmed, some filled with sediments from catastrophic backflooding. Others were drowned, their upper reaches preserved as submerged features. Today, as ships tow echo sounders over the Mediterranean floor, as seismic lines slice the subsurface, those forms still stand out, over-deepened channels, collapsed canyon walls, weirdly oversized river mouths. They are the long, quiet memory of a brief, violent rearrangement. This is one reason geologists trust landscapes when they reconstruct old environments. Even when the water itself is long gone, the shapes it left behind are stubborn. They outlive climate phases, species, even mountain ranges. With the right tools, they can be read like a palimpsest. One story written over another, older ink still faintly showing through. The Messinian Crisis also offers a window into how science itself moves. When the first hints of enormous buried salt deposits appeared, they were disturbing to the accepted picture. A normal sea wasn't supposed to do that. Early proposals of a nearly dry Mediterranean sounded extreme, even fantastical. Over time, more data came in. Cores confirmed the salt. Microfossils told of stressed hypersaline conditions. Seismic lines mapped canyons deeper than any reasonable fluctuation in sea level could explain. Models of water budgets showed that, under realistic climates, you really could drop the basin far below its outlets if the gateways pinched. Each new line of evidence nudged the consensus away from "this can't have happened" toward "something like this must have happened," and finally to "it almost certainly did happen," though we're still arguing about the details. Even now, the story is provisional. Different teams emphasize different mechanisms: single pulse versus multipulse reflooding, nearly complete desiccation versus persistent deep brines, simple versus complex gateway behavior. New surveys shift the conversation. A core from an unexpected location overturns a neat narrative. The Messinian Crisis is a reminder that scientific understanding is not a set of finished answers, it is a moving front. The questions become more precise, the uncertainties become better framed, the pictures sharpen, but they remain pictures, not photographs. For a subject like this, unfolding on timescales so large they're almost anesthetic, that slow refinement feels oddly appropriate. The Earth took hundreds of thousands of years to push the Mediterranean past its threshold, and a similar patience is required to untangle what happened. Yet there is something immediate here, something you can carry with you, even as you drift towards sleep. We live on a planet full of thresholds, gateways that seem narrow and unimportant until they close, balances that hold for a very long time and then, once tipped, seek a new equilibrium in ways that are anything but gentle. The Mediterranean is full now. Its waves lap against beaches lined with cities. Ferries cross its straits. To stand on its shore today is to feel a sense of permanence. But under those calm waves lies a record of a time when that sense was entirely wrong. The basin that looks eternal has been a desert, a salt pan, a brine trap, and a roaring waterfall's destination. It has flipped, more than once, between very different realities because of small, persistent changes in climate and tectonics. Knowing that, you might find yourself looking at other parts of the world a little differently. An ice sheet margin, a narrow strait between two seas, a shallow shelf where waves break over sandbars that once were land. You might wonder, which of these are closer to their own threshold than they appear? Which quiet systems around us are slowly being pushed towards some new state, their future already written in equations of flow and balance, but not yet visible on the surface? And as you close your eyes, with the imagined echo of distant waterfalls still fading, you might let one gentle question linger. What other seas, what other landscapes, are quietly waiting for their moment to change? So we end where we began, with a sea that looks calm, inevitable, permanent, and the knowledge that it is none of those things. Over the course of this story, you've walked through a full cycle. First, the quiet narrowing of gateways, Africa creeping north, the Gibraltar Passage tightening, evaporation slowly pulling more water from the basin than the Atlantic could replace. Then the Messinian Crisis itself. Water levels falling, shorelines stepping down, a great blue interior sea turning in places into salt flats and brine pools, rivers cutting toward a base level far below anything that exists today. Life retreating to refuges, improvising around extremes of heat and salinity. Beneath the later sediments, beneath the modern waves, that phase is still there in thick white and grey bands of rock salt. A frozen memory of years when the Mediterranean behaved less like an ocean and more like a gigantic landlocked desert lake. After that came the pause, a basin partly emptied, partly filled with dense, stagnant waters, a landscape of chasms, plateaus, stranded deltas, a strange, otherworldly version of the place where cruise ships and fishing boats now drift. And then, at last, the return. At Gibraltar, the balance tipped the other way. The sill dropped, or global sea level rose, or some combination of both. Atlantic water found a path over the threshold and began to fall. Whether you imagine the Zanclean flood as a catastrophic curtain of water roaring into the basin in weeks, or as an intense, sustained inrush over months or years, the effect is the same on geological timescales. A nearly empty bowl meets a full ocean. The physics do the rest. Water accelerates. It scours the seafloor. It carves new channels into old ones. It chases dry air up canyons that had only just adjusted to their strange sub-oceanic depths. Former river valleys reverse their logic overnight, turning from pathways of outflow into conduits of invading seas. Salt plains are drowned. Shorelines race up slope. The basin, which had taken hundreds of thousands of years to empty, refills in the blink of a geological eye. By the time things settle, a familiar pattern is back in place. A deep, connected Mediterranean, trading water and heat and salt with the Atlantic, hosting a new web of ecosystems, writing a new set of stories in mud and shell and sand. Yet the old stories are still there, hidden. Tonight, if you picture the modern Mediterranean, you might imagine it from far above. A dark, quiet shape between continents, dotted with a few boats, the glow of harbour cities around its edges. Under that surface lie the ghosts we've been following, kilometres of salt stacked and folded, canyons twice as deep as anything the present sea level could explain, now filled and buried, wave-cut terraces that once faced open air, now pressed into shadow at the edge of continental slopes. Every gentle wave that breaks on a beach in Sicily or Spain or North Africa is passing over that history. Over thresholds crossed and recrossed, crises survived, states flipped and flipped back again. It's a soothing thought in its own way. The sea you know is the latest version, layered over many others. It has vanished, in essence, and returned before. It has endured tectonic shoves, climate swings, and episodes that would have seemed unthinkable to any creature living on its shores at the time, and yet here it is, murmuring against the coasts as if it had always been this way. As you drift towards sleep, you can let that image settle. Slow, regular waves moving over hidden salt and drowned valleys, over the scars of ancient waterfalls and the quiet outlines of buried cliffs. A surface that looks simple, floating above depths full of unanswered questions. Because even after decades of drilling, mapping and modelling, parts of this story remain unresolved. How close did the basin come to true desiccation? Was the reflooding a single, overwhelming pulse, or a series of surges and pauses? How did the sudden return of a deep-sea ripple through global climate, through ocean chemistry, through the evolution of life along these shores? These aren't closed chapters. They're live debates, written in data and hypotheses, and new surveys still being planned. The Mediterranean's past is not a finished tale. It's an unfolding investigation, and it leaves a lingering feeling. If something as solid-seeming as a whole inland sea can wink out and roar back, what other parts of our planet are more provisional than they appear? You might carry that thought lightly with you, or let it fade along with the day. Before you go, if you found yourself drifting with this story, if the idea of vanished seas and hidden thresholds helps you relax or sparks your curiosity, you might consider tapping like, leaving a comment, or subscribing so you can find your way back here next time. I'd also love to know where you are in all of this. If you feel like sharing, drop a comment with what time it is for you right now and where in the world you're listening from. A coastline, a city, a quiet room far from any sea. It's a small way of mapping our own human ocean of listeners onto this ancient basin story. And if you enjoy sinking into these deep time mysteries, there's a whole book of prehistoric secrets waiting for you at sleepytimehistory.com. You can read more there, or pick up a copy to explore other worlds that once existed on this same planet. Vanished rivers, lost continents, climates that would feel like dreams. For now, though, the Mediterranean is full again. The gateways are open, the thresholds are for the moment stable. Above, the surface is dark and calm. Below, the rocks remember everything. Let the waves roll over those buried memories steady and slow as the questions soften and your thoughts drift. The sea has returned. The mystery can keep watch while you rest.